Hey everyone, how's it going? In this video, we're going to look at word embeddings. It's sort of the state of the art when it comes to things dealing with text, especially text classification. Before we start looking at word embeddings, we're going to look at something slightly different. I think it'll help us, though, understand a little bit of kind of the basic idea or the motivation behind what word embeddings are. And that thing I'd like to look at is something called matrix factorization. We'll see it at work. I'm not going to go into details about kind of the mathematics of how it works. It's pretty easy to implement, really. That I will put in a PDF associated with this video. And the example I'd like to look at is how to make music recommendations. So let's say we own a vinyl shop and people come in and we're going to try to make recommendations for them. And how can we make these recommendations? Well, one way is called collaborative filtering, and this has been around for a really long time, and it's sort of the way Amazon works. So if you see a product, you're looking at something, you might see something like, people who bought this also bought that, or people who looked at this item also looked at these other items. That's making the power of the customer looking at what all these people are doing and helping us build this collaborative filtering system. And we'll see that in a second. So let's say someone comes into our shop and says, I like Taylor Swift and Carrie Underwood. How do we make that recommendation? So in one class I taught, I played 5-minute snippets of different musical tracks, one by Maren Morris, one by Major Lazer, Tim McGraw, and so on, and had the people rate these on a scale of 1 to 5, how much they liked these tunes. And here are the little chart that shows part of the data that we have. And let's say someone comes in and says, I like Major Lazer. I'd rate Major Lazer a 5, Haley Steinfeld a 5, Janelle Monáe, didn't really like her, a 1, Keith Urban a 5. And the task is, one we've had in that NumPy video, is trying to find the nearest, someone that's really close to Anne. And we might find that Michaela Goldrich is pretty close. So she also rated Major Lazer a 5 and also rated Haley Steinfeld a 5 and Keith Urban a 5. And they were only one off on Janelle Monáe. So they're really pretty similar. And then we go and look at, what does Michaela like? Maybe Anne would like that person. And Michaela said Tim McGraw was a 5, so we'd recommend Tim McGraw to Anne. This is sort of the basic idea of collaborative filtering. You can see it's a fairly simple idea, but it's a very powerful one and one that works pretty well. There's nothing wrong with this method. Now let's look at a different approach to making recommendations. Let's say someone, instead of saying, I like Taylor Swift and Carrie Underwood, says something like, I like rhythm and blues music. In that case, we'd have a chart like this. So we'd have these various musical artists, and let's say the people in our shop, the workers, all rated them. Are they rhythm and blues artists or pop artists? So we got this genre label for each artist. And we know that, those genre things don't really work too well in machine learning techniques, so we might give them just numbers. Right, so the rhythm and blues is a 1, pop is a 2, and so on. And then we also learned from some video that, having integers doesn't work because that implies a distance, and, that implies that rhythm and blues is closer to pop than rhythm and blues is to rock, because that's 3 away, rhythm and blues and rock, and only 1 away from pop. So that doesn't make any sense whatsoever. So we did something called one-hot encoding. That's fine, and we learned that one-hot encoding is a sparse method, right? Because there's 1 in the rhythm and blues section and then 0s in all these others. So if someone comes in and says, I like rhythm and blues, we can do that. We can make these recommendations. So we can look on our chart, see which artists are rhythm and blues, and make those recommendations. So that's if someone comes in and says, I like rhythm and blues. Another approach is to kind of go back to our original idea. So if someone comes into our shop, says, they like some artists like Dua Lipa, and then we mentally think, is Dua Lipa a rhythm and blues artist, a pop artist, or whatever? And we make that mental calculation, and we see that she's a pop artist. And we may recommend other pop artists. So we kind of do a mental calculation. Dua Lipa is a genre, and we make recommendations based on that genre. In this case, we'd recommend Taylor Swift. As if this person never heard of Taylor Swift before. But anyway, so that's the basic idea. So that's genre-based in a slightly different way, just based on kind of one feature of each artist. But what happens if we even got more involved? What happens if we kind of categorize things with lots of features? And that's what Pandora, at least in its original kind of inception, did. Right now, Pandora is a pretty complex website with lots of algorithms and lots of modes of interacting with the music. But originally it was you would create a station, you would give that station a seed of here's one song I like, and then it would go off and find other songs and populate that radio station. How Pandora did this was they had what's called the music genome. It's 450 attributes of music. There'd be things like beats per minute. Was it swung 16th notes or not? What was the gender of the lead vocalist? What was the level of distortion on the electric guitar? All these different features, 450 attributes. Each song they have in their catalog, they would rate by these 450 attributes, and it would take quite a while. It took a trained musician 20 minutes to analyze a song. This was a professional, trained person that did this, not just some run-of-the-mill person, but a person who has a solid background in music theory. They write on their website, the typical music analyst working on the Music Genome Project has a 4-year degree in music theory, composition, or performance, has passed through a selective screening process, and has completed intensive training in the music genome's rigorous and precise methodology. To qualify for the work, analysts must have a firm grounding in music theory, including familiarity with a wide range of styles and sounds. All analysis is done on location. So the takeaway here is that the person doing this analysis is a highly trained professional person, right? An expert in doing this classification. And how then Pandora would use this information after all these experts spent hours and hours and hours and hours and hours categorizing this huge catalog would be it would work like this. So I would create a radio station, I would seed it with a song, maybe Hilary Hahn's J.S. Bach Partita for Violin Solo No. 1 in B minor, and then off Pandora goes and tries to find, using algorithms we talked about. They have very complex algorithms, but you can imagine even a simple one like the nearest neighbor approach of finding music with similar genomic features, and then they'll play those tunes. Right? We have the option then in Pandora to kind of, I don't really like this one. It can do kind of subtraction. Well, maybe the person really didn't like these sets of features. We can kind of eliminate them, but we can do this learning of these seeds. So now we see how this would work if we have these experts coding this information. But as I said, it takes hours and hours and hours and hours and hours, even though they still do this, and it's a very useful technique. Let's imagine a computer doing it. And with a computer doing it, instead of an expert, we're not going to be interested in things like beats per minute, swung 16ths, gender of the lead vocalist, although we could, right? We could kind of have a computer analyze the actual audio track of some music and make these kind of feature distinctions. But we're not going to do that at all. Instead, we're going to look at a very simple chart like one I showed you before, where people were rating artists. Maybe they're just rating it with an up arrow or a down arrow, but we have some sort of rating for these. And then from there, we can start extracting what are called latent features, hidden features. We don't know what the features are, but we're going to have the computer just figure them out. So let's say we say we want 50 latent features. It would look like this. Taylor Swift has a rating of 25 on latent feature 1, 59 on latent feature 2, whatever. So the computer is going to figure out what the value of all these different features are for each artist. Hopefully artists that are similar will group together. So like Taylor Swift and Dua Lipa, they're going to group together a bit. And that would be the hope of our algorithm. So what's amazing about matrix factorization, something that kind of blows my mind that it can do this, is it can take one matrix, the matrix that's shown on the top, right, of the ratings different customers have for different artists, and from that, it can infer or determine two different matrices. One is how much various customers like these different latent features, and the other is for each artist, or for each track really, what are the values of these latent features. It's just totally amazing that it does this. It's through gradient descent. It's cool. Check it out. I'm not going to go into detail. So what we've seen now are kind of different methods of doing this, right? We have one method where we have human experts determine the features. Again, as I mentioned, these were highly trained people, and they took 20 minutes to classify songs or tracks based on 450 features. The other method is to have computers figure them out, figure out these latent features, these hidden features. So what does this have to do with text classification? Glad you asked. So let's take a look at some text. Here's one. This is in LinkedIn, just a description about a person. And my name is Sam, and I'm a globe-trotting software developer. I've trekked through tropical forests and camped in deserts, climbed Mount Kilimanjaro, and scuba dived in the Red Sea, slurped soup dumplings at night market street stalls, and gotten lost in too many cities to count. My latest adventure led me to Seattle, where I joined blank, blank, blank. A much more interesting life as a software developer than I have had. So one method, as we've talked about in the previous video, is to convert these words into integers, right? We're just going to assign each word an integer. And so if name occurs a bunch of times in our document, it's going to have the same number, 400. And does occur throughout this a few times. So and is number 2, and we see it occurring in different spots in that for the first line, in the third line, and in the last line. And they're all given. So these integers represent the different words in the document. And here's those comparisons with what they did. So and is number 2, is number 3, and so on. And as we get further up, here are the numbers. But as we talked about in the music example and kind of throughout all these videos, and as you can see, these numbers are don't mean anything, right? So in this aspect, or in this example, globe is close to soup, right? They're both 5,700 something. And sea is really far away from scuba, and they seem maybe sort of related. So, these numbers are just kind of arbitrary and really don't represent things. So in the last video, we did one-hot encoding, where we created a limited vocabulary set, like maybe 10,000 words, and just one-hot encoded each word. So for my name is Sam, and I'm a globe-trotting, I forget what it was. We take each word, my, and that's one-hot encoded. So that array is 10,000 long, and in one spot there's going to be a 1, right? So that'll be the my column. That represents the word my. So there's 9,999 zeros and 1, 1. My name is also has a 1 somewhere, the column representing the word name, and there's 9,999 zeros, and so on. So that's kind of the idea of one-hot encoding that we've talked about in the last video. And as I've mentioned a number of times, that's a sparse matrix because everything's 0 except for one column that has a 1 in it. So suppose we do something a little bit differently, something like that music genome project that took a track of music and analyzed it and came up with 450 features. Maybe we could reduce each word, like the word cat or dog, into a set of semantic features that mean something. And that's what we're going to do, or that's one option we have. So we can take a word like woman, and we have different features there in the rows, animate, human, female, and adult. And we can say woman is plus for animate, plus for human, plus for female, plus for adult. And the semantic features for girl are that a girl is animate, human, and female, but is a minus for adult. And a man is minus for female, and so on. So we can have this idea of features, and each word can be represented, instead of that sparse matrix idea of there's a 1 somewhere for the word woman, we'd have 1s for animate, human, female, and adult. Maybe 450 different features for each word. So that's the idea of kind of trying to come up with the underlying semantics of a word. So instead of this, where we have this typical music analyst, as I mentioned, has tremendous training, we would need kind of linguists to come through and analyze each word, determine the semantics of a word, and here are the 450 features of each word. And people have done this. So this is an ontology, the Microcosmos ontology, developed by Sergei Nuremberg. He became kind of famous with this ontology, and coming across that, we have everything on the left, and that's divided then into objects, events, and properties, and so on. So eventually in this huge ontology he develops, we're going to figure out what a woman really means by different features. And this was really popular in the 90s. Lots of places developed it. So MIT developed ontologies. ARPA developed this knowledge sharing effort library. And you can see Microcosmos there toward the bottom. So it was a really popular idea that we'd have human experts look at words and analyze them and kind of determine the semantics or the true meaning of a word. So that most of those dropped out. They became unworkable in different ways. There's sort of one major holdout, which is Scicorp. which is, as they say, a revolutionary AI platform, which a lot of it is hand-coded knowledge about words and how words are related. Kind of a cool project. My claim to fame is I interviewed there. It was an extremely tough interview, and I didn't get the job. But that's a story for another day. So how all these work is that we have human experts, linguists mostly in this case, and it's going to be similar to Pandora and the Music Genome project, right? So we're going to have them create a bunch of features, 450 features or whatever. But people have been working on this, linguists have been working on this for hundreds of years. Lexical semantics. What is the meaning, or how can we represent the meaning of words? And once we have a schema, it's going to take hundreds and hundreds and hundreds of hours of human expert time to create these features of each word in our dictionary. Maybe we have 100,000 words in our dictionary, so that's going to take a huge amount of time. But in matrix factorization, we saw a different way of doing things. We had the computer figure out these latent features. Maybe we can use that information. So we're going to have latent features a computer determining the features of each word automatically. And that is called word embeddings. It's a very common word now, or phrase now, word embeddings. You'll hear it over and over and over again. If you continue working this, just think of it as this is a computer that's going to identify kind of the latent semantic features of each word. And we can say, well, give me 100, 200, 500 different features. So we can specify the length and have the computer figure out, what is the meaning of this word. So in the music examples, we had, how people rated things, and that's what created these latent features. How are we going to train, or how is this computer going to learn what the meaning of each word is? Well, it's based on something Firth said in 1957. You shall know a word by the company it keeps. So we can determine the semantic features of a word by looking at the surrounding words of that word. So if words are similar, you'd think they'd have similar left and right contexts. Let's take a look at these examples. These are just very trivial ones, but kind of lead us and give us a general idea of how this will work. So I went to the bank to deposit my check, and I went to the credit union to deposit my check. You can see here that I went to and to deposit my check kind of surround, both lines. And we can think that, well, maybe bank and credit union are sort of the similar things. We would want to give them similar semantic features. Or the second example, if we see piano concerto, violin concerto, cello concerto, we can start thinking, well, maybe piano, violin, and cello are similar in some way. They can all precede concerto. So that's kind of the idea behind how the computer is going to do this. It's going to look at words around the word we're interested in, let's say bank, and it'll look at, the context, left and right context of a word, and determine, what features other words in that context have. And we as people can do this fairly easily, or we can make predictions about missing things. This was an article about just a recent one from the Washington Post about voice actors for video games, and now they're doing the voice acting from home. And so that was kind of a cool, interesting idea. And here are some of the sentences in that article. I think I was able to make blank expressions and noises that in a normal setting my body would be like, don't. And so can we figure out what that blank is? And the answer in this case is to make facial expressions. So it's facial expressions. It's the one that's missing. And maybe you predicted that. So let's look at the next example. It was like, wait a blank. We can just go back to these people and have them pop out of their family room into the closet and record some VO lines. And that one's a pretty easy one, I think, right? We can all see that should be a minute. So how do we do this? Well, we've kind of, in our brain over the years, we've developed all these latent features. We know what words, depending on the context, we shall know a word by the company it keeps. We can make good educated guesses about what words are missing. We do this all the time if we're in a very noisy environment, when there's at a cafeteria or restaurants that are very noisy and people are talking to us. We may miss a number of different words in what that person's saying, but we understand it perfectly well by making educated guesses. Or we're missing kind of parts of the word, or the person doesn't articulate one word very well. We can still recover the meaning of these words. And the last example, the on-the-fly evolution of several standardized processes did carry some blank benefits. According to both blank developers, blank actors, on the development blank, Voigtnac noted that some people seemed more willing to contribute their opinions to the creative process when they didn't feel the blank of speaking up in a formal meeting. So let's see how everyone did. The on-the-fly evolution of several standardized processes did carry some fringe benefits according to both the developers and actors. On the development team, Voigtnac noted that some people seemed more willing to contribute their opinions to the creative process when they didn't feel the pressure of speaking up in a formal meeting. So again, these are from the article, Call of Duty Voice Actors Spend the Summer on Video Calls Like the Rest of Us, Game Development During COVID, from the Washington Post. All right, so what this shows, other than I've read that article, is that we can figure it out from just based on context, and that's pretty much how the learning takes place in determining word embeddings. And the hope is that words that are similar are going to group together in this latent feature space. This is kind of a two-dimensional image of it, but we would think that flowers and trees are similar, and maybe programming languages, but like Python, JavaScript, and Java. And violin is kind of close to electric guitar and acoustic guitar, but the guitar ones are closer together to each other than they are to violin, and so on. So that would be the idea, that things would be kind of close together. And these latent features are going to represent the meanings of the different words. So instead of doing this one-hot encoding, where we're going to limit the vocabulary to 10,000 words and then do the one-hot encoding of it, we're going to just have word embeddings. So my is going to be reduced to 500 feature values, name 500 feature values, and think that this is no longer sparse, right? In the original idea, we had a 1 somewhere representing this is the word. But in this example, the real simple example with the word woman, we know that's going to be, plus feminine, plus human, plus whatever. So we know that, it's not a sparse matrix anymore. There are values for many of these features. So in word embeddings, there are two basic things we need to do. One is training, where we go through the text and we learn from the different words, what the embedding should be, what those features, these latent features are. And then once we know those, we can use that information. So we see a word, we just look up what that feature vector is, that word embedding is, and use that. In some cases, when our data set is very small, maybe we don't have enough information to do that training very well. It won't be a very accurate training. In that case, we can use pre-existing word embeddings. There are a number of these available that we can download and use, and these are just models of people examining very large corpora and coming up with what the word embeddings should be. So that's it for the general overview of what word embeddings are. We're going to get into kind of the nitty-gritty of it, or the hands-on of it, when we go to our associated Jupyter notebook. So I hope this was extremely helpful, or you got the rough idea of what word embeddings are. And be sure to check out and do that hands-on of that notebook. So thanks very much for watching. Take care. Bye.